Good morning again. I think it's time to start. So in the last lecture, we discussed the procedure of canonical quantization, where we have essentially replaced the Poisson brackets for fields and the momenta of the fields with quantum Poisson brackets that are commutators. And we have also discussed the construction of the Fock space, which is an infinite-dimensional Hilbert space constructed by successive application of creation operators to the vacuum state, to the unique vacuum state. And today I'm going to develop these operator concepts. And before I continue with the new material, let me ask if you have some questions concerning the material of the previous lecture. Okay. If you don't have questions, then we continue. So now we come to the question about the Hamiltonian. And in the classical theory, we know that the Hamiltonian we derived can be written in terms of creation annihilation operators in the following way. So H was found to be integral over momenta, the frequency A star on P, A on P. That was a classical expression for the Hamiltonian. If you do a similar computation for the Hamiltonian H in quantum field theory, of course, now you know that A star and A will be replaced by A dagger on P and A on P. But you have to be careful here because these two operators, A dagger and A, they do not commute with each other. Do not commute. And therefore, the order of these operators in any operator expression, which you construct with the help of this A and A dagger, matters. So the order matters. And for the case of the Hamiltonian, one accepts to write the following expression for the quantum Hamiltonian now, A dagger on P, A on P, meaning that operator A dagger stands on the left from an operator A on P. And this way of ordering of this operator A and A dagger is called normal ordering. Is called normal ordering. In other words, normal ordering is a rule of ordering of operators A and A dagger in such a way that operators A dagger are always go to the left or always stand on the left from the operator A. So in other words, if you have some expression from operators A and A dagger, let me write something like this, and then you apply to this expression the procedure of normal ordering, then this expression should go to A dagger, A, A. And I recall that the order of operators A between themselves and A daggers between themselves does not matter because operators A commute between themselves and A dagger also commute. So their relative order does not matter. But what matters is that all A daggers stand on the left, put on the left from operators A. And to symbolize this way of ordering, people use the special notation which is called normal ordering, and they write double dots on the left from the expression which you're going to normal order, and to the right of it. So this expression in the normal ordered form then is given by this expression here. And the same idea of normal ordering is also applied to fields. So if you have a set of fields, say phi1 on x1 and so on, phi n on xn, and you would like to normal order their product, that would mean that in the resulting expression, you first of all, you will write all the fields in terms of creation annihilation operators, and then you put all creation operators to the left from all annihilation operators. And the idea of adopting such ordering prescription goes to the fact that the energy of any state in Fock space becomes a well-defined quantity. In particular, vacuum carries zero energy, because if you apply H to the vacuum state, then that would be an integral dp omega on p a dagger on p a on p acting on a vacuum. But since vacuum is annihilated by operator a on p, then the result of application of H to the vacuum state will give you zero. On the other hand, if you write the Hamiltonian in the opposite way, if you assume antinormal ordering, for instance, where you put a dagger to the right, then in fact your Hamiltonian will create first a one particle state out of the vacuum, and then you will be annihilating this one particle state by means of operator A. And as you see, in order to compute the result of this section, you would need to commute A on P through A dagger on P, which will result into the delta function on zero, because it would be delta function P minus P. So this is delta function evaluated at zero, and this is actually infinite, as we know. And in this case, you see that the action of the Hamiltonian on the vacuum state will give you a nonsensical equation, because the result of application will give you just zero. So in order to prevent this problem with defining the Hamiltonian on any state in the Fock space, just to make it well defined, you may apply this normal ordering prescription. So it's very important to remember about this, that in quantum field theory for operators acting in the Fock space, one usually uses the normal ordering prescription. In particular, you do this for the Hamiltonian in order to render the energy of Fock states well defined. Now, if we look again at our field phi, then in terms of creation annihilation operators, the field phi, which now is an operator, has the following expansion. This field has the following expansion. So first of all, you have this measure factor. If you write it with all H bar and C constants, and this looks like this, and then there is 2 omega on P, and then creation operator A dagger on P, exponential I over H bar ET minus PX, plus A on P, exponential minus IH bar ET minus PX. And if you now take this field phi on X and consider, say, the negative frequency part of phi on X, so negative frequency would be the piece which corresponds to, let's see, to this expression here, negative frequency, well, let's take positive frequency part, rather positive frequency. So I don't want to deal with this annihilation piece, but I will look at this piece which contains a dagger. And this piece I will denote as phi plus. And I consider this phi plus at time t equals to 0, just at 0 moment of time. Then phi plus and x at 0 moment of time will be given by just creation operator multiplied with exponential prefactor, exponential minus I over h bar, p multiplied with x. And now allow me to take the vacuum state and act on this vacuum state by operator phi plus. Then this is what you get, and you get essentially a one particle state. One particle state. So application of the positive frequency part corresponds to creating a one particle state. And in particular, if you now take another one particle state with a non-trivial momentum p, and I will take bra state. So this is one particle state with momentum p, so particle carries momentum p. Then you see that if I take the scalar product of p with phi plus x0 vacuum, then the result of this section will give for me the following expression. So I will be having c divided by 2 pi h bar in the power 3 over 2. And then integral exponential. Let me see how I will write it. So I will write first dp square root of 2 omega on p, and then I will have a state p, a dagger on p. Well, I need here actually to distinguish. Let me denote the variable over which I integrate. Let me denote it by q, because it's a dummy variable over which I integrate. So there will be now q here and the q here, and then 0 and exponential minus I over h bar. And then here we will have q with x. So q is a running momentum, is a dummy momentum over which we integrate, and p is some fixed momentum which defines this one particle state. And so this you can compute, this quantity you can compute. It will give you, so you need to write down an expression for p, for a state p. And you remember what is this? This would be an operator a dagger. Essentially, this is proportional to an operator a dagger acting on a vacuum conjugate, which means that you will have vacuum a on p. So essentially, this is a state. And so when you plug it in here, in this scalar product, then you will be commuting a on p with a dagger on p, so moving a on p to the right vacuum to annihilate it. And as a result of this evaluation, so you need to evaluate a dagger on q. Let me write more explicitly. So what you will have a on p here, a dagger on q. And when you make this commutation, you will obtain the delta function on p minus q. And also from the normalization of a state P, you will get that this should be divided by, to be exact, by 2 square root of omega on P. So when you plug this expression, in this, actually it should be multiplied. It should be multiplied by square root 2 omega at P. So when you substitute this expression into this integral, then you will see that the result of this evaluation will become simply an integral of a delta function. And so when you integrate a delta function, you will find that you get minus I over h bar P with x divided by 2 pi h bar in the power 3 over 2. And this expression you, of course, recognize from quantum mechanics. You know what is this? This is a wave function. There's nothing else as a wave function of a free particle in quantum mechanics. From quantum mechanics, so this is expression is a wave function of a free particle, moving with momentum p, free particle with momentum p. So in other words, the procedure of applying the positive frequency part to the vacuum, positive frequency part of our scalar field to the vacuum, creates out of a vacuum a particle with a standard quantum mechanical wave function, exponential minus I h bar px, which corresponds, as I said, to free particle moving with momentum p. So our operator phi plus creates standard quantum mechanical particles in this Fock space construction. Now, let me make also a comment, as I promised, about the procedure of constructing the Fock space, which also is known under the name second quantization. So if somebody tells you second quantization or uses this term second quantization, then you immediately should understand that this is about Fock space. This is about the Fock space realization of field operators. Now, the Klein-Gordon equation, which we have solved and which we have studied, actually was introduced already by Schrödinger himself. So this is Schrödinger who introduced it. And his motivation for introducing Klein-Gordon equation was rather simple. Basically, we know that we have for relativistic particle the standard relativistic dispersion relation, E squared divided by square of the speed of light minus P squared minus M squared C squared is equal to 0. And so this is the relation which we call mass shell condition, but in fact, this is a dispersion relation for relativistic particle, which relates energy of this particle with its momentum. And Schrödinger's idea was simply to pass to quantum mechanics by replacing P, this free momentum, with an operator of momentum, which is minus I h bar d over dx, and replacing energy with I h bar d over dt. So energy is replaced essentially by the time derivative, as energy is in fact is an eigenstate of the Hamiltonian, and the Hamiltonian generates time evolution, so shifts in time, while momentum is responsible for the space shifts, and it's realized as a derivative d over dx. And so after this replacement, now on the left-hand side of this dispersion relation, you discover the Klein-Gordon operator. So if you do this little calculation, you see that what you get is 1 over c squared second derivative with respect to time minus d over dx. No, let's write it d over dx I squared, sum over I, 1, 2, 3. No, and then plus you need also m squared, c squared, and then since these operators contain h bar, they come with h bar squared, you need to divide by h bar squared. So instead of the usual mass shell condition, which is formulated in terms of numbers, E and P are numbers, or P is a vector and E is a number, now you have a second order differential operator. And in a way, the natural substitution of the dispersion relation would be to take this differential operator and apply it to the wave function phi. And so, in fact, then you can say that what you have here, on the one hand, mathematically, you are studying the kernel, you are defining the kernel of this operator, kernel of this wave operator. So phi belongs to the kernel of the wave operator. On the other hand, from mathematical, from, so to speak, physical point of view, rather than mathematical, but from physical point of view, what we are writing then is a Schrödinger equation for the wave function phi. So you can say that what you have obtained is a Schrödinger equation. Schrödinger equation. Schrödinger equation for the wave function. For the wave function phi. And the fact that this equation contains second order derivative in time rather than first derivative in time is due to the fact that you are dealing with relativism, that you are dealing with relativistically invariant theory, which puts time and x space variables, in other words, on equal footing. So since they are on equal footing and they are rotated into each other by means of Lorentz transformations, the second derivative derivatives in the space directions are accompanied by second time derivatives in the time direction. So in a way, this is a relativistic version of the usual non-relativistic Schrödinger equation, and this is an equation which defines for you the wave function phi. This would be okay, but when you define this wave function by means of this equation, you would like to continue with the usual quantum mechanical analogy for this wave function phi, then you run into a number of problems. You immediately run into a number of problems. Especially in the case when you also switch on non-trivial interactions, so self-interactions for this theory. To clarify this, let me introduce, instead of a real field, actually a complex field, because complex field is more suitable to treat, to regard it as a wave function, right? Because wave function in standard quantum mechanics is a complex function, the complex valued function. So if I pass from a real scalar field to complex scalar field, then the action for this field is written in the following way. So it's very similar to what you have for a usual real scalar field, except that now this expression also involves also involves a complex conjugate field in order for the action to be real. So it's written in the following way: d mu phi star, where phi star is just a complex conjugate of phi, minus mc over h bar squared phi star phi. This is how the action for a complex scalar field looks like. Now, similar to what you have in non-relativistic case, you can introduce two important quantities. One of them is probability density, rho. Probability density. And another is the probability current. I denote it as J. Probability current. Probability current. And these quantities are defined explicitly where this complex field phi as follows. So rho is IH bar divided by 2mc squared. 2mc squared phi star time derivative of phi minus phi time derivative of phi star. And the J probability current is given by minus h bar with I divided by 2m phi star gradient of phi minus phi gradient of phi star. Why these quantities are introduced? Because as in the non-relativistic quantum mechanics, you can see that these quantities satisfy the standard continuity equation. d rho over dt plus divergence of probability current J is equal to 0. Continuity equation which is satisfied due to the Klein-Gordon equation. It reduces to the Klein-Gordon equation for a field phi. When you plug rho and J into this formula, you will see that you will get 0 because Klein-Gordon equation is satisfied. Or in other words, it's satisfied due to this equation for phi. And an analogous equation, of course, you can write for phi star. Okay, so it looks like you up to now you follow the standard paradigm of usual quantum mechanics. You introduce rho and J, probability density and probability current, and you see that continuity equation, they satisfy the continuity equation as you would like to have this quantity in the non-relativistic case. In fact, you can also understand that what is written down here is nothing else as the written down explicitly the covariant form of the current conservation, where J mu is a four current with components C rho and J. So it's a four current, probability four current. And this current is conserved on equations of motion. This is simply a direct consequence of Noether's theorem. Noether's theorem. Because the existence of this conserved quantity is due to the fact that the action for relativistic complex scalar field has the following symmetry. Phi goes to exponential I alpha multiplied by phi, where alpha is a constant parameter. So there is a symmetry. You see from this expression that if you change field phi by multiplying it with the phase, and simultaneously you change phi star by multiplying it with the conjugate phase, then this phase disappear, it cancels out, and the action is simply invariant with respect to these transformations. So this is the symmetry of the action, and by Noether's theorem, as you know, this symmetry must correspond to a conserved current, and this current exactly this probability for current which I'm writing here. So on equations of motion, which is a Klein-Gordon equation for phi and phi star, this current must be conserved, and this is exactly what you can verify by direct means. So up to now, everything is fine. The problem is, however, that probability, so expression for probability, which you would like to think as probability density, is not positive. So rho is not positive. So it has a deficiency. Rho is not positive. In contrast to the expression for rho, which you have in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, rho is defined as a product phi star with phi. And this is an explicitly, manifestly positive density. So it can be given an interpretation of probability density, because probability is always non-negative. Why it is the case? Why rho is not positive? You can see it from this expression, from an explicit expression for rho. That is because now in the relativistic case, you deal with second order differential equation. And since you deal with a second order differential equation, supplying it and solving it, you need to supply it with initial conditions. And since it's of the second order, you need to supply as initial conditions not only the value of phi, but also the value of its time derivative at an initial moment of time. And this value of phi and phi dot can be chosen in an arbitrary way. And if they can be chosen in an arbitrary way, so phi and phi dot, you see that this expression might also be taking negative values, and therefore rho is not anymore positive defined in general. Actually, rho goes in the non-relativistic limit when speed of light tends to infinity. It goes to the density of non-relativistic quantum mechanics. This can be explicitly traced by using the expression for phi in the so-called WKB approximation, and this expression for phi then starts from IMC squared, something like this, MC squared, and then there are corrections to this expression. And so when you consider multiply by psi non-relativistic of non-relativistic theory, then you see that, and then time also here, then you see that when you will be differentiating with respect to time, time derivative, for the first time, it will meet this expression here, and it will be not acting on psi. It will just produce for you MC squared multiplied by psi, the wave function of the non-relativistic mechanics. And then from this expression here, phi star dt phi, you will see that at leading order in the limit c to infinity, you will actually get psi star multiplied by psi. And time derivative will disappear because of acting on this term here. So rho is nice in all respects, that it's a part of the conserved for current. It is a quantity which has a correct non-relativistic limit, but it loses one important property, which allows to interpret it really as a probability density, namely it's not positive anymore. And therefore the whole interpretation, quantum mechanical interpretation of this quantity as of, in particular, of phi as a quantum mechanical wave function is not possible. And all this picture becomes especially, how to say, shaky with this interpretation of rho as probability, especially if you switch on interaction. Then you can show that for sure rho cannot be served as a probability density, quantum mechanical probability density. Okay, and the correct interpretation of field phi actually has been found later by Pauli and Weisskopf. And according to Pauli and Weisskopf, the field phi must be treated as an operator rather than the wave function. And that's what we have done when we treated phi, when we quantized phi and treated phi as an operator. So for us, phi is not a wave function, but rather phi is an operator, which then should be used to define with its help the amplitudes and as a consequence creation and annihilation operators, which are used to build the Fock space of this scalar field. So Fock space representation. So we naturally come to the Fock space representation, treating phi as an operator, because this operator should act in some space. And the natural space where it acts is a Fock space. So we naturally come to the Fock space. And such a treatment of phi as an operator acting in the Fock space is exactly what is called second quantization. And historically, I mean, this term is historical because when you say second quantization, in a way, you think that under the first quantization act, you replace the classical scalar field by would be a wave function phi. So this would be a first quantization, would be, let's put it in brackets, would be a wave function, just like Schrödinger did. And this would be a wave function, would be the first quantization act. No, because it's like you are passing from classical theory to quantum mechanics. You say, oh, now it was a classical field, a classical thing, now I replace it by the quantum mechanical wave function. So I do quantization process. And phi now is interpreted as a wave function, but in fact, it's not a wave function. So I need to quantize it again to promote it to an operator acting in some Hilbert space, which in this case is a Fock space. So phi, making phi an operator, would be what we would call the second quantization act, or simply second quantization. Promotion of a wave function to an operator acting in the Hilbert space. So we quantize the wave function, and that's why this is called a second quantization. Well, today, perhaps is not a good thing to talk about first quantization, second quantization. We just know that we have to treat phi from the very beginning as an operator acting in the Fock space. And in this respect, we just refer to this as quantization of the scalar field as a process by means of which we directly put in correspondence to a classical field an operator, and then for this operator we construct a representation. We represent it in terms of creation and annihilation operators acting in the Fock space. Well, in any case, this explains this historical meaning of the term second quantization. Do you have any questions here? This is what I wanted to tell you about this term second quantization. Okay. If this is sort of clear, then we come to the discussion of commutation and Green's functions. Commutation and Green's functions. Now, in the theory of interacting fields, even in the classical theory, you know that solutions of inhomogeneous field equations with point-like sources play a special role. And these solutions of such inhomogeneous equations with point-like sources, they have a special name. They are called Green's functions. And as you know from the classical electrodynamics, Green's functions can be of different nature. For instance, there could be retarded Green's functions or advanced Green's functions. And in particular, in quantum field theory, we will be interested in the so-called causal Green's functions, which are also known under the name Feynman propagator. And now I would like to discuss how these functions are defined and explicitly constructed for the case of the Klein-Gordon field. Therefore, what I need to consider here is Klein-Gordon field, an equation of Klein and Gordon with sources. But before I do that, I start from solutions of the Klein-Gordon equation without sources. And this is related to the notion, this is related to such objects as commutators of quantum fields at different space-time points. And since we are talking about commutators and these functions, sometimes they are referred to as commutation functions. And you asked me already such a question is, what is the commutator of quantum fields at different space-time points? Not at the same time, where the commutation relations are canonical, those which we have already discussed and considered. Now, it is time to ask ourselves, so what are commutators of fields at different space and time points? And the first very important commutation function, which we are going to discuss, is the so-called Pauli-Jordan function. Pauli-Jordan function. So this function is defined in the following way. We just compute the commutator of the field phi on xt, so which is an operator now, with phi on x prime and t prime. So at different space and different time points. And it gives us some non-trivial function where for simplicity I single out some prefactor made of this h bar and c, and then some non-trivial function d of x minus x prime, where here x is a point in the four-dimensional space-time. So x is a point which carries, so x is xt, and x prime is x prime t prime. Okay, so time and three components of spatial components of vector x are encoded in one notation, x and x prime here. So this is Pauli-Jordan function. By definition, it's a commutator of two quantum fields at different space-time points. Now, as we will see, this d is a function. It's not an operator. Although we are computing operator, but the result is, in a sense, you can say it's a C number, which is some number or some function multiplied with an identity operator, and identity we are never right. So this is D then comes out as a usual function on space-time, depending on space-time points. Now, before yeah?
Why the D have to be a function of argument x minus x prime?
And that is something which we will see. We will prove that it depends only on the difference x minus x prime. It depends not separately on x and x prime, but it depends on the difference between x and x prime. Actually, it has, yes, so before I do the derivation, I sketch the derivation, I'll write an explicit form, what we are going to find. Since dx minus x prime depends on one argument, I can write it as d on x. That's a unique argument of d. And what we are going to show is that this function explicitly is given by the following formula. Epsilon depending on t divided by 2 pi. I will tell you what is this epsilon by t, depending on t. Then there is a delta function on x squared on the 4 interval, minus 1/2 mc over h bar squared. Then there is a Heaviside theta function on x squared. And then there is a Bessel function, J1, depending on mc over h bar square root of x squared, where x squared is a 4 interval, divided by mc over h bar square root of x squared. This is how this Pauli-Jordan function looks like. Okay, where x squared, actually we can write also what is x minus x prime squared. This is a 4 interval, standard 4 interval. So this is c squared t minus t prime squared minus x prime squared. So standard 4 interval. What else? So theta on x, theta depending on x, is a Heaviside theta function. Heaviside step function. Let's call it step function. J1 here, J1 is a Bessel function, J1 on x, a Bessel function with index 1. And what else we need is epsilon, right? Epsilon on t is defined as a difference of Heaviside theta functions like this on positive and negative values of t, and explicitly it is defined in the following way. So it's +1 if t is bigger than 0, it is 0 if t is 0, and it's -1 if t is less than 0. So this is a step. So it's, okay, let's write 1 here, 0, -1, it is like this. Epsilon on t and t here. So this is epsilon, and theta is a standard Heaviside theta function. So theta on t is defined as +1 if t is bigger than 0, and it's 0 if t is less or equal to 0. Okay. What we see from this formula is that, first of all, because of the presence of this prefactor here, because of the presence of the prefactor, d on x turns out to be 0 if t is equal to 0. So at t equals to t prime, d on x turns out to be 0. So this means that the equal time commutator vanishes, which is good because it shows that it's compatible, of course, with the fact that for the one and the same time argument, fields commute. So f on xt and phi on xt and phi on x prime t, equal time commutator of the fields, we know that it vanishes, and this is the result of canonical quantization. This is how canonical Poisson bracket requires us to have when we pass to the quantum theory under the procedure of canonical quantization. So this is canonical expression. So this is okay. So this is compatible with what we know. The second feature is that you also see that commutator, according to this answer, the commutator of two local fields vanishes if their space-time points are separated by the space-like interval. So if x squared is space-like, which means x squared is less than 0, that's what it means, space-like. Maybe I should be more exact here by saying that we are talking about x minus x prime squared less than 0, then Pauli-Jordan function vanishes as well. That is what you see from here. This first term is delta function on x squared, and so if x squared is less than 0, then you don't meet support of delta function, and so delta function then is 0. And also Heaviside function. So this term here, if x squared is less than 0, then the Heaviside piece, or piece containing this Heaviside theta function, vanishes as well. And so the whole Pauli-Jordan function vanishes for points separated by the space-like interval, and therefore fields which are separated by such an interval, they commute. And this is, in a way, if you wish, implementation of causality principle in quantum field theory. So this is an important fact, which is manifestation, let's say manifestation of causality principle in quantum field theory. Why it is so? That's because, as you know, no signal can propagate faster than the speed of light. And this means that if I have two events or fields which I would like to measure at points which are separated by the space-like interval, then measurement of field in one point and the measurement of the field in the other point, they do not correlate because these measurements are completely independent. Signal is not enough to propagate from the point x, where you make a measurement of the field phi, to the point x prime, where you make a measurement of the field x prime. So in other words, field values separated by the space-like interval, they are independent observables. And we know that if we have two independent observables, in order to be able to measure them, according to the basic principles of quantum mechanics, they must commute. They commute. And that is exactly what we see here. So fields separated by a space-like interval are independent observables because they are lying in causally disconnected regions. So indeed, from this computation, we see in a way manifestation of this causality principle. Now, maybe a last comment about the explicit expression, which we are going to find by means of computation, is that expanding the Pauli-Jordan function around a light cone, so expanding Pauli-Jordan function around light cone, cone, we will find the following expression. So d on x will behave itself around light cone as minus epsilon t divided by 2 pi. And here we will have delta function on x squared that we cannot do anything with this. And then minus 1 over 2 mc squared over h bar squared, sorry, mc over h bar squared, and then there will be Heaviside theta function x squared plus corrections. So essentially what we are expanding here is this piece where around light cone means that we are expanding this function around x squared or square root of x squared being 0. So when x square root of x squared tends to 0, because x squared equals to 0 defines for us a light cone, is what we call light cone. So if you do this expansion, then the ratio j1 to this square root of x squared goes to 0, sorry, goes to 1, and therefore expansion starts from these expressions here. And we see, in fact, that on the light cone, so when x squared is equal to 0, we have severe singularities for this Pauli-Jordan function. So passing through the light cone, d on x experience singularities of two types. One of them is just delta function singularity, and the second type of singularity is finite discontinuity, is given by this function theta on x squared, so finite discontinuity. No, this is something which you usually understand as jump. So function jumps because of this theta function. So it's not there inside light cone, and it's equal to 1 outside light cone, so you have a jump. And on top of that, there is this also delta function singularity in delta on x. So singularities of this d function are, in fact, of d on x are concentrated on the light cone, as you see from the explicit expression. And now you can ask yourself how to derive these results, so in particular, how to construct this function. And so let me briefly explain how you do it. Maybe I will do all these steps schematically rather briefly, and you may do the thorough computation of this either yourself or during the seminar. You can ask Dima to do with you in a thorough way. So step number 1, we just use an expression for our fields in terms of oscillators. So we start from this expression, from this commutator, x prime t prime, given in terms of creation annihilation operators. So up to prefactor, which contains c, 2 pi, h bar, we will get the following: dk prime. So 3-dimensional integrations, and then there will be 4 omega prime omega depending on k, and omega prime depending on k prime. And then there will be commutators of A on K, and A dagger on K, A on K prime, like this. And I omega T minus omega prime T prime minus I K X minus K prime X prime. And another term where A commutes, A on K commutes with, have commutator A on K with A dagger on K prime, like this. Multiply also minus I omega T minus omega prime T prime, plus I K X minus K prime X prime. That's what you get. So this is essentially, you see that field phi contains A dagger and A, two terms, and here there are also two terms, A dagger and A. Dagger commutator is equal to 0, commutator A with A is equal to 0. So what is left over is a commutator of this A dagger depending on K with A depending on K prime, and another commutator of A depending on K with A dagger depending on K prime. And this is exactly what I have written down here. So you use Fourier decomposition of phi's, and then you come to this formula. Next step is obvious. You use commutation relations between these oscillators, quantum oscillators. So you replace them by delta functions. And then you can integrate one of the delta functions. You can integrate the corresponding delta function. So this will be proportional to what? To delta function k prime minus k prime. And the other commutator will be proportional to minus delta function k minus k prime. And then you can integrate over k prime by using these delta functions, simplify a bit, and as a result, you will find the following expression. So let me write the exact coefficient, I h bar c also minus 2c divided by 2 pi cube integral dk over 2 omega multiply with exponential ik x minus x prime multiply by sine function omega t minus t prime. This is what you will get because of the minus sign, so you can combine the terms with exponential I omega t exponential minus I omega t, which will produce for you sine omega t minus t prime. And so if you now compare this with the definition of the Pauli-Jordan function, you see that this prefactor I omega I h bar c you also have here. So dx then from this expression is identified as minus 2c divided by 2 pi cube integral dk over 2 omega on k exponential ik x sine omega t. So this what is the subject of your further computation. This is how you get it out of commutators. So this is the next step, is to continue the computation and actually evaluate this three-dimensional integral or evaluate it in terms of some known functions, like for instance, a Bessel function. So how you proceed? It is convenient here to come to spherical coordinates. Spherical coordinates, so you introduce a quantity r, which is a square root of x squared. and k, which is square root of k squared. And you orient your coordinate system along direction of k. So this would be k, this would be vector r, no, vector x with length equal to r. And then in between, so this is my coordinate system then, like this. And I will introduce angle theta. So this is a spherical coordinate system. This is standard angle phi, theta, and r. And therefore, what you will get here for d on x in spherical coordinates, you can write in the following way. So minus 2c over 2 pi cube. Integral from 0 to infinity. Let me see what I'm doing here. I think I have to do it actually opposite way. So I have probably to take, right, since I'm integrating over k, so I will direct r here along z axis of the coordinate system, and its rather will be vector k here with the length k, with the length equal to k, and this will be angle theta and the phi, right? So then it gives me integral from 0 to infinity k squared dk, so passing to coordinate spherical coordinates to omega sine omega t. This is what is left over, and then I integrate over angle phi from 0 to 2 pi, and from 0 to pi I have to integrate sine theta d theta, that forms a measure, multiply by exponential, and then there is this scalar product, exponential I kx, which is now a scalar product of two vectors r and k. So it's exponential I length of r multiplied by length of k multiplied by cosine of angle between them. So cosine theta. In other words, I have here r k cosine theta. Okay, that's what we have. And this integral can be elementary computed. You see that the measure sine theta d theta is minus d on cosine theta. And cosine theta is what you have then too. What you have in this exponential. So that can be elementary integrated, and then integral over d phi is also elementary taken. And therefore, d on x upon this integration becomes minus c divided by 2 pi squared r. And that comes from this k r here. Integral from 0 to infinity k dk divided by omega sine omega t, and the integral over theta from 0 to pi will produce then upon integration sine function of kr. So this is now how your integral looks like. So essentially, this means that you reduce evaluation to the one-dimensional integral. And this you can further write conveniently in the following way. So you write c divided by 2 pi squared 1 over r d over dr integral from 0 to infinity dk divided by omega. Omega, by the way, is a function of k, sine omega t, so omega is a function of k, that we remember, cosine kr. So when we will be integrating back over r this cosine, it will turn into a sine, but it also produce k, that k that was here originally. And that's the reason that you now differentiate over R, you get rid of this K, which was standing alone, but now it's not in this expression anymore. Okay, so this is what we do. And now we can actually remember what this omega is. Now you see, this integral is a bit non-trivial. It's not so easy to take because omega on k is an explicit function of k, which is not so pleasant function. It's a square root of k squared plus omega plus m squared. So m is this, let's write mu squared, where mu is mc over h bar. Yeah, so it's not so pleasant quantity. Although this is now k squared, you can write as a length k squared plus mu squared, as we agreed. And so explicitly d on x, then if I substitute this expression for omega, then d on x take the following form. So this is 1 over 4 pi 1 over r d over dr integral. I allow myself to integrate from minus infinity to plus infinity, so I extend integration for negative values of k because the function which I integrate is even. And then I divide the integral by 2, and that's why this 2 here turns into 4 pi squared, 1 over 4 pi squared. Integral from minus to plus infinity, dk, then there is this omega, and omega is square root of k squared plus mu squared. And cosine kr, and then there is a sine, and t is what is t? T is x0 divided by c, and omega divided by c is exactly this square root, k squared plus mu squared. So I can write this therefore as sine x0 square root of k squared plus mu squared. So this is integral, one-dimensional integral, which we have to take. You see, it's quite non-trivial because it involves this k in this way under the square roots. And the way to proceed is looking at this expression. You see, it is convenient to introduce a function f depending on r and t. So r and x0 or t, whatever, because x0 is ct. It's a function of two arguments, r and t, and simply define it as 1 over pi integral from minus infinity to plus infinity, dk divided by square root k squared plus minus mu squared cosine kr sine x0 square root of k squared plus mu squared. Then this function, if I differentiate it over r and multiply by 1 over r, essentially should reproduce for me this d on x. And so this function which I have to compute. And to proceed, of course, we need to find a clever choice of variables which somehow should efficiently deal with these square roots of k squared plus mu squared. And the way to do it is to introduce the following change of variables. So k, I write as mu multiplied by sine, not sine, sinh of a new angle phi. Well, it's not actually an angle, it's just a variable, which is supposed to run from minus infinity to plus infinity, because in this way, sinh of phi will cover the full range of the variable k, also from minus infinity to plus infinity. You remember sinh is this function So it behaves like this. So there will be one-to-one map with this function from a 5-line to a k line, from 5-line to a k line. So it's a good change of variables. And why this is efficient? That's because if you now compute k squared plus mu squared, you see that this is square root of k squared. So this is mu squared sinh squared phi plus mu squared. Mu you can take out, and then you get a square root 1 plus sinh squared phi. But you know what is sinh squared? 1 plus sinh squared is cosh squared. So you get mu square root of cosh squared phi. But this I can take the root explicitly because cosh phi is manifestly positive function. So this is everywhere for any phi. And this is always positive. So I can take a square root without any problem out of it. And moreover, you see that if you take measure dk, it will give you mu cosh phi. And this mu cosh phi from the dk cancels exactly with mu cosh phi, which you get in the denominator from this square root. So the whole measure dk over square root k squared plus mu squared will go to d phi. It's very convenient. Huh? So the same as this function f on RT. So function f on RT under this change of variables takes the following form. 1 over pi integral from minus infinity to plus infinity d phi cosh of what? Cosh of k multiplied by r, and k is mu r sinh phi, right? So this is k. Let me write it again, sinh phi. And then there is sine, and here is not cosh actually. This is cos, this usual cos. It was cos here, cos of this expression. And then there is sine. So function f on RT is given by 1 over pi integral from minus infinity to plus infinity d phi cos mu r sine phi multiplied with sine mu x0 multiplied with cosh of phi. Here sinh and here cosh, sinh and cosh. And now, so we have this integral, but this we can further use the formula for the product of two trigonometric functions, cosine multiplied by sine. So we proceed and write it as 1 over pi, 2 pi, integral from minus infinity to plus infinity d phi. And then this is sine mu r sinh phi plus mu x0 cosh phi minus sine mu r sinh phi minus mu x0 cosh phi. And then the bracket is closed. Okay. So then product sine by cosine, I write as a difference of two sines. And so the first considerations, the first step in our next considerations is to start distinguishing three different cases depending on inequalities between x0 and r. For definiteness in further computation, I will consider the case where x0, which is the same as CT, is bigger than R, and then R is bigger than 0. And that is needed because every time I pick up a certain inequality between the CT and R, I have to make its own change of variables in order to proceed. So for the case which I'm considering here, the relevant further change of variables I need to do is x0 divided by square root of x0 squared minus r squared is equal to cos phi 0, so hyperbolic cosine of phi 0, r divided by square root of x0 squared minus r squared is equal to hyperbolic sine of phi 0. So once again, a new change of variables is needed. And this is needed in order for me to turn these sums here of cinches and coches into something simple. And indeed, if you do this further change of variables here, then the expression for phi RT takes the following form. This is 1 over 2 pi integral from minus infinity to plus infinity d phi sine. And then under sine, I will get the following. So mu square root of x0 squared minus r squared. This is a prefactor I'm taking out. And then using this change of variables and the summation formula for hyperbolic cinches and coches, I will get here cosh of phi plus phi 0. And analogously, in the second sum, where I need to take minus out, I will get mu square root of x0 squared minus r squared, cosh, the same cosh, phi minus phi 0. And an interesting point is that since I'm integrating over all phi, in the first integral, you can make a shift of variables phi by minus phi 0 to remove this phi 0 from integration. And in the second integral, you can make a change phi plus phi 0 to remove this shift. And so then the integrals are equal to each other. So the answer doubles and gives you 1 over pi integral from minus to plus infinity d phi sine of mu square root x0 squared minus r squared cosh phi. And now, finally, if you look at the books into the integral, looking for an explicit integral representation for the Bessel function, then you see that what is written down here is exactly the Bessel function, integral representation for the Bessel function g0 mu square root of x0 squared minus r squared. Now, okay, so we achieved our goal. So we reduce this function f on rt to something unknown. And this known is just a Bessel function of index 0. And if you now do this calculation for other inequalities between CT and R, you will find the following combined answer. You can do it yourself or during the seminar. So you will find plus J0 as mu square root of x0 squared minus r squared for the case when CT bigger than R. That's what we have done. Then you will find that the answer is actually 0 if CT in between R and minus R. And finally, you will see that you will get minus G0 mu square root of x0 squared minus R squared. For the case of CT less than minus R. So 3 possible cases of inequalities between the value of CT and R, and for each of them, you will get the corresponding answer for this function f. So these 3 results for f on RT can be combined in one expression by saying that f on RT is given by epsilon on T multiply with theta function CT squared minus R squared. So CT is x0. I recall that this is x0. So CT squared minus R squared. And then G0 on the argument MC over H bar square root of x0. So that means CT squared minus R squared. Now, and the final step consists in evaluating d on x, which is derivative of this expression with respect to r, multiplied with 1 over r, And so what we get is epsilon on t divided by 4 pi r d over dr on this expression here. So theta CT squared minus R squared, J0 MC over H bar square root CT squared minus R squared. And so when you differentiate it over dr, differentiating of this term will give you delta function, which you have seen in the expression for delta on x, and then differentiating the Bessel function with 0 index, with index 0, will produce you the Bessel function with index 1. So there is a standard formula for that. And so finally, you will find this expression for the Pauli Jordan function. Delta function minus 1 over 2 MC over H bar squared. Now I'm writing this mu, so this is the same as mu. Theta on x squared, G1 MC over H bar. This is in fact square root of the 4 interval divided by MC over H bar, square root of the 4 interval. So we have derived an explicit expression for this Pauli Jordan function. Okay, that's what concerns this important commutation function, which is called Pauli Jordan function, and which is a commutator between quantum fields at different space-time points. So this is how this commutator looks like, and this is answers the question which you asked me some time ago, and how this goes. Any questions?
Professor, I have a question.
Yes.
This function of Pauli Jordan, can you discuss the physical interpretation of the infinite discontinuity in the light cone? Why? From the physical point of view?
From physical point of view, you are passing a first situation where your causality disconnected regions now start to pass in causal contact. And in fact, along the light cone, you see signals propagate with the speed of light. And this is where you see this effect as a, for instance, jump in a sense that all the way till light cone, the fields commute, so they are independent observables. No, and suddenly, when you are passing through the light cone, the results of measurement at one space-time point inside light cone can influence the measurements in the other point inside light cone. So you don't have any more in causally disconnected regions. And so these results have a certain, I mean, these measurements might have a certain correlation, which is exactly reflected in the appearance of this non-trivial function, which exactly undergoes certain trouble when you pass it through the light cone.
Oh, thank you very much.
Mm-hmm. Okay. Okay. In fact, what you can further show is that, well, you see that what we have achieved is that we have computed this commutator phi x t phi prime phi on x prime t prime, and we found that this is I h bar c, this Pauli Jordan function x minus x prime. You can then show that since x prime and t prime are different from x and t, you can act on both sides of this relation with a wave operator, with a Klein-Gordon operator, which is 1 over c squared d over dt squared minus d over dxi squared plus mc over h bar squared. You can act on both sides. So then delta, since you can act, say, with respect to the points x and t, this box gets inside the commutator as an act on a field phi on xt. And since phi is a solution of the Klein-Gordon equation, then this is 0. And therefore, on the right-hand side, you have to find that the result of applying box with respect to, say, coordinates x and t to Pauli Jordan function also gives you 0. So, in fact, what we have obtained also is an explicit solution of the Klein-Gordon equation. So this is how solution of the Klein-Gordon equation looks like. This is a particular solution of the Klein-Gordon equation, which reflects this causality principle. As soon as points x and x prime are space-like separated, so this means that, okay, so you can write this also as delta xt dx is equal to 0 by putting x prime to 0. You see that what you have obtained a particular solution of the Klein-Gordon equation, which satisfies these causality principles that delta on x is equal to 0 as soon as x squared is less than 0, as soon as point x squared, as soon as x is outside the light cone. And this is how this solution looks like. That's another interpretation of the Pauli Jordan function. It is a solution of the Klein-Gordon equation with this property, with this causality property. In fact, this is a very, very good exercise, which I recommend you to do, is to prove that this is indeed a solution. So you forget about the derivation we have done. You just take this function, d on x, given by this expression, and you hit it with a Klein-Gordon operator, and then you differentiate, you apply derivatives to this generalized function, to delta function, theta function, Bessel function, to show that at the end, when you apply this operator, you will obtain 0. This is a very good exercise to do. It will tell you a lot about the nature of these generalized functions and how to deal with them to properly show that this is a 0. So this is a very good exercise to do. To show this explicitly by starting from the explicit expression for the Pauli-Jordan function. Okay, I think that is probably enough for today. So today was a bit technical. Indeed, this derivation of the Pauli-Jordan function is a bit technical issue, but I find it very important because it, in a way, that encodes the causality principle for quantum fields. Causality principle for quantum fields. So in the next lecture, we continue and consider retarded and advanced Green's functions, which would be a solution of the Klein-Gordon equation, but now with a point like source on the right-hand side. And also to the most important, probably, of all the functions in quantum field theory, namely to the Feynman propagator. Consider the Feynman propagator. But for today, I think that is all. If you have questions, please go ahead.
I have another question, Professor.
Yeah.
Concerning the name of second quantization. I read in the lecture notes of David Tong. He has a different opinion about this. If I understood correctly, Professor Tong said that the name second quantization, from the physical point of view, is wrong. It is only for historical reasons. Because he said
that's exactly what I said. That agrees with what I said. That goes for historical reasons with the wrong interpretation of what Klein-Gordon field is. That's why I tend not to use this word second quantization, but you can read about it in the books. So that's why I'm explaining where it arose, from which source it arose.
Okay, thank you very much.
No, it agrees. It agrees with what I said. Because people thought that maybe phi first a wave function, just like wave function of non-relativistic quantum mechanics, but this is wrong. But this is wrong because phi is actually cannot be the wave function for the reason that it leads to probability density which is not positive definite, not always positive definite. And then people say, okay, maybe we should consider phi the wave function under the first quantization act, and then second quantization act promotes it to operator. But in fact, you can escape all this. You can just not to say all of this and forget about this word second quantization. Say from the very beginning that you quantize classical field, it becomes an operator, and you use it to build up the Fock space representation. That's it.
Perfect. I understood.
Okay.
So I have a question about. So first, we have a classical Klein-Gordon equation, and we find some classical solution, and then we quantize them and calculate the commutator of this quantized field operator and get this D, which is a propagator. And that is again a solution to the Klein-Gordon equation. So,
yes.
Why we didn't get this at the beginning when we calculate the solution to Klein-Gordon equation as a classical.
Well, when we solved the classical Klein-Gordon equation, you remember that in this solution we got arbitrary amplitudes, which are this A and A dagger, A and A star. So we get a solution for amplitudes. We get a solution with arbitrary amplitudes, A and A star, right? And we did not specify them because we said that we consider all possible initial conditions, and the amplitudes can be specified only by imposing some extra conditions on these amplitudes. Otherwise, these amplitudes become dynamical variables, which we further would like to quantize that treat them also as operators. Now, we also get a solution of the Klein-Gordon equation here. But in this solution, which I'm now writing as this d function, d on x, these amplitudes are fixed by the, if you wish, by the conditions of causality. So what we found here is a particular solution of the Klein-Gordon equation. Particular solution of the Klein-Gordon equation where a priori arbitrary amplitudes A and A star, which should be fixed by imposing some conditions, for instance, initial conditions. Here they are fixed by imposing the conditions of causality. You see, so this is a particular solution where the amplitudes are fixed in such a way that what we are getting here is a causal solution. And actually, this solution, you see, we constructed by, in a way, departing from the quantization conditions which we imposed, right? Because in our solution, what we have used, we used commutation relations between A and A dagger, which result to us into delta functions. And in a way, you see, these quantization conditions remove the amplitudes completely. And then we proceed with our calculation and end up only with these waves, which we eventually integrated out and got some explicit function on space-time, which, according to this consideration, starting from the origin of this D function, led us to the conclusion that D must be a solution of Klein-Gordon equation. There is no any other way it cannot be, because it originates from this commutator of field phi, which itself was constructed as a solution of the Klein-Gordon equation with arbitrary amplitudes, A and A star. But imposing the quantization conditions, this A and A star go away. They are replaced by delta functions because of imposition of this canonical commutation relation. And then we get a concrete solution of the Klein-Gordon equation, which in fact, where in fact you might think about the general solution in which amplitudes A and A star has been explicitly solved for this causality condition. So we get a particular solution of Klein-Gordon equation. There are other solutions. I'm not saying that this is a unique solution. No, all solutions we obtained in terms of arbitrary amplitudes A and A star, but causality requires a particular solution to appear here, which satisfies these causality relations.
Okay, understand. Thank you.
Okay. Okay, so if you don't have any further questions, then we continue next Friday as usual. Then I wish you a pleasant day, and till next time, bye-bye.